Managing access to Kubernetes cluster can quickly become complex, especially as teams grow and security demand increases. Traditionally, Kubernetes rely on a static kube config and tokens that don't scale well and pose security risk. Modern enterprises require centralized and dynamic authentication solutions that integrate well with their existing identity infrastructure, providing secure and manageable access controls. Hello everyone, I'm Sanskriti Harmak, a developer relations at Vultr, and in today's Tech Talk, we will explore how Kubernetes can delegate authentication to OpenID Connect, understand why Okta is a great fit for this model, and how you can implement this pattern on Vultr Kubernetes Engine. Lastly, we'll wrap it all up with a hands-on demo that walks through the entire integration process in action. So, without any further ado, let's get started. Let's start with the why. Kubernetes doesn't manage user identities directly. It delegates that responsibility to external systems. By integrating with a provider like Okta, admins can control access to all clusters centrally with roles and groups synced automatically. Users can also authenticate using their organization wide credentials and gain access to multiple systems, including Kubernetes, that improves both security and user experience. As teams grow and change, access right can be granted or revoked based on group membership. And with multi-factor authentication and conditional access policies enforced at the identity layer, you're no longer relying solely on what's configured inside the cluster. OIDC or OpenID Connect is the standard protocol for modern authentication. It is built on top of OAuth 2.0 and designed specifically to share who the user is and not just whether they are authorized. When a user authenticates, Okta issues JSON Web Token, which is a signed identity token that contains claims about the user. For example, who they are, their email address, group membership, and more. Kubernetes doesn't need to validate password or issue token itself. It just trusts the identity token provided via OIDC. This decouples authentication from Kubernetes entirely, allowing it to rely on trusted providers like Okta while still enforcing fine-grained authorization through native RBAC. Pairing Okta OIDC with Vultr Kubernetes Engine delivers significant benefits for managing cluster access. By mapping Kubernetes roles directly to Okta groups, you ensure consistent access policies across all your services. The use of short-lived scoped tokens reduces the risk of leaked credentials by eliminating long-lived secrets stored on user machine. With Okta as your unified identity platform, users can seamlessly authenticate whether they are accessing the dashboard, CLI, or cluster, all while maintaining a single source of truth for identities. Also, this integration provides an audit-ready architecture, as all user actions are tracked centrally through Okta's logging and security tools, helping you meet compliance and governance requirements. Altogether, this setup combines the flexibility of cloud-native infrastructure with the strength of enterprise-grade identity controls. Let's now walk through a live demo showing the full integration flow from user authentication through Okta, token issuance, to access verification inside a VKE cluster. We'll see how browser-based login flow works, how Kubernetes validates token, and how access policies are enforced in real time. Before we begin, let's make sure that our prerequisites are covered. To follow along, you'll need access to an Okta account with admin privileges. This is important because only admins can manage applications, configure identity providers, and assign users to groups, all of which are essential for configuring OIDC with Kubernetes. If you don't already have an Okta account, we have attached a link in the description below where you can sign up for a free Okta developer account. This gives you full admin capabilities in a sandbox environment where you can test integrations like these. Once you have an Okta admin console, you can even invite your team members to your organization. For that, navigate to the people page present under directory. Here, click on add person. You will be prompted to enter a few details along with an email address and asked to set user to the group. Optionally, you can set their roles or admin permissions. As a part of the setup, you will also require an API token. To generate that, head to the API page present under Security. Here, switch to the Tokens tab and click on Create Token. Provide a label to your token and decide the origin from where the API calls can be made. Once done, Click on Create Token and store it somewhere secure. Also ensure to note your organization name and base URL. You can retrieve those details from the Profile Information menu present on the top right corner in the Okta admin console. Once these pieces are in place, your organization is ready to act as a centralized identity provider with role-based access before we integrate with Vultr Kubernetes Engine. We also have a code samples repository where we upload all our configuration files, manifest or scripts used during demos and walkthroughs like this one. It serves as a reference point for anyone following along or trying to replicate the setup later. The link for the same is attached in the description below. Now, let's go ahead and open our workstation to continue with the setup. Let's start by cloning the repository and navigating to the relevant working directory. In this directory, you will find terraform.tfvars. This is where we will define variables required by Terraform to automate identity integration setup with Okta. Open this file using your preferred editor. You will be prompted to feed in values for some variables. Let's break these down to understand better. Org name is your Okta organization identifier, typically a part of your subdomain. Base URL is the root domain URL your tenant is hosted on. For example, okta.com. API token is a secure token generated in your Okta admin console. Terraform uses this token to authenticate API calls for user and application provisioning. Admin email is the email address of the user who will be granted full admin access to the Kubernetes cluster, whereas restricted email is the email address of a second user with fewer privileges. This is used to demonstrate RBAC enforcement. Once these values are configured, let's move ahead with provisioning of OIDC integration using Terraform. Before we proceed, please make sure that Terraform CLI is installed on your machine. First, we'll initialize Terraform with Terraform init. This command sets up the local environment and ensures that Terraform has necessary plugins to interact with Okta's API. Next, we'll validate Terraform configuration to catch any syntax error or missing fields. You should see a message like this, which confirms that your HCL files are written correctly and ready for execution. Before applying the configuration, it's always a good practice to verify the planned actions. This command outputs an entire execution plan showing what will be created, updated, or destroyed, giving you a chance to verify that everything looks correct before making changes. Finally, to provision the Okta application and related resources, we will run Terraform apply. You will be prompted to confirm the configuration. Type yes when ready. Once Terraform finishes applying the configuration, let's switch over to the Okta admin console to verify that all necessary resources were created correctly. In your Okta admin console, navigate to the groups page present under directory. Here you will find two groups created by Terraform. First one is called KTS admins, second one is called KTS restricted users. This group is mapped to a Kubernetes cluster role binding, giving full administrative privileges inside Kubernetes cluster, whereas the members of this group are granted limited scoped access inside Kubernetes, typically restricted to non-destructive actions like viewing or modifying their own resources. Next, head to applications, and here you should notice a new application created by Terraform called VK OIDC. This application acts as the OIDC client that facilitates token-based authentication between Kubernetes and Okta. It is registered as a web-based application that supports confidential client flow and handles client secrets. A new authorization server is also created by Terraform called KTS Auth. This is a custom authorization server with required claims for Kubernetes to validate users and their group memberships. Under claims, a claim called groups is defined to include only group names that start with KTS. This ensures that only relevant information is injected to ID token. An access policy called KTS policy is also present that defines how and when tokens can be issued to the VK OIDC application. Now that we have verified that all our resources are created as intended, let's switch back to our workstation. We now have the required OIDC configuration details as output by Terraform apply. So we are ready to use them while provisioning a Kubernetes cluster on Vultr. Let's begin by exporting a few environment variables to make our API request more readable. First, we'll export Vultr API key. Then OIDC issuer URL, and lastly OIDC client ID. We'll be using Vultr API directly to make a post request to the Kubernetes cluster endpoint to spin up a VKE cluster with OIDC authentication enabled. Here we are providing a label to our cluster. This cluster will be deployed in the New Jersey region. We are referring to the latest Kubernetes version, but if you're curious and want to explore the available versions, then you can simply make a GET request to the Kubernetes versions endpoint. In the OIDC block, we are passing the newly created Okta authorization server's issuer URL. Kubernetes will fetch the metadata from here. Here goes the client ID created by Terraform for VKE OIDC application. Username claim tells Kubernetes which claim from the token to treat as user's identity. We are using sub, which is a unique subject identifier. Groups claim specifies which claim will list user's group. In the node pool section, we are defining the initial number of nodes in the pool. You can even enable autoscaler, which will in turn activate the minimum and maximum number of node bounds. And each node associated with that of our Kubernetes cluster will have a compute size of 2 virtual CPUs and 4 GB of memory. Once all the values are set as per need, let's hit the API call to provision the Vultr Kubernetes Engine cluster. Once the call completes, there are two ways you can check the status of your provisioned Vultr Kubernetes Engine cluster. Either you can make a GET API request to Kubernetes cluster's endpoint using the ID returned in the API response, or simply head to the Vultr customer portal and click on Kubernetes present under product section. Here, as we can see, our newly created VKE cluster is up and running. Let's click on it to open its overview page. From here, we can download our Kubernetes configuration file by clicking on download configuration. Once downloaded, let's move the config to the default Kubernetes directory. Next, let's verify that our machine can talk to the VKE cluster. This should return a list of available nodes in the cluster if everything is configured correctly. Kubernetes itself doesn't natively support OIDC token acquisition. It expects token to already exist in your kube config. To bridge this gap, we'll use oidc-login plugin. It allows kube control to dynamically fetch ID tokens from Okta whenever you run a command instead of relying on static manually issued tokens. And to install this plugin, we'll use Krew, which is the official plugin manager for kube control. It simplifies discovering, installing, and managing community-supported plugins like OIDC-login. Let's create a helper script to install Krew. You can paste the exact code snippet for the same from the supporting documentation attached in the description below. Once done, save the configuration and exit from the file. Make the script executable and run it. Then add Krew's install directory to your path. You can also add this line to your shell configuration file so it persists. Finally, let's install OIDC-login plugin using Krew. After successful installation, let's apply Kubernetes RBAC configuration for both admin and restricted users based on Okta group membership. The KATS directory contains 3 YAML files. KATS admin crb.yaml binds the built-in cluster admin role to KATS admins group, giving full access across the cluster, whereas this file defines a custom cluster role called restricted pod access, allowing basic pod operations like listing, creating, or deleting pods. KATS restricted user crb.yaml, on the other hand, binds that role to the KATS restricted users group to enforce restricted access. We'll apply all the configurations at once. Now that the RBAC configurations are successfully applied, simply run this command to clear any previously cached login state. Now that our cluster is provisioned and OIDC is configured, let's set up Kubernetes access for our Okta-backed users. We'll focus on the admin user, which is mapped to the KATS admins group in Okta. First, we'll fetch the Terraform output values and store them as environment variables. This includes OIDC issuer URL and OIDC client ID. You can fetch the OIDC client secret value directly from the Okta admin console or simply run this command and then export the value. If you're unsure of the context name, use kube control config get contexts. It will list all the available clusters on your account. So retrieve the value and export the cluster name from here. Let's finally define kube control credential entry called admin user that uses OIDC login plugin to authenticate via Okta every time kube control is invoked. This command passes OIDC issuer URL, client ID, and client secret, all required for secure token exchange. It also requests extra scope like profile and email. The flag OIDC client secret is required because the type of our application, VK VKE OIDC is configured as web, but if you're using native app, then you can omit this flag. As we can see, the admin user is set. Next, let's bind this admin user to our VKE cluster context. Let's now run a simple command to verify that OIDC-based authentication is working as expected. This command serves two purposes. It triggers the OIDC login flow, which in turn launches a browser window where you will be redirected to your Okta login page. Once you successfully authenticate using your Okta admin credentials, OIDC login plugin retrieves a short-lived token and passes it back to kubectl. If everything is configured properly, kubectl will use this token to authenticate with the Kubernetes API server and return a list of nodes in the VKE cluster. In a similar fashion, you can configure Kubernetes access for users in the KTS restricted group by creating a separate kubectl context and binding it to the appropriate credentials. For step-by-step instructions, please refer to the supporting documentation linked in the description below. To sum up, integrating Okta OIDC with Vultr Kubernetes Engine delivers a modern and secure authentication experience that scales with your team and enhances operational security. If you're ready to try this yourself, then get started today with the $250 in free credits using a promo link attached in the description below. We also encourage you to join Vultr Community Forum, where you can connect with fellow developers, share your experiences, ask questions, and get direct support from the Vultr team. Thank you so much for joining this Tech Talk. We hope this empowers you to build more secure and manageable Kubernetes environment with confidence.